finished up last time, we were talking about stage 3 in our titration, which is where we have a equilibrium established between our acid and our base. Now that we're continuing with this, we're going to talk about going beyond the equivalence point, but it is good to kind of digress here for a moment and talk about this area right here. So you can see when we hit this equilibrium point, if we're going from a weak acid, we're starting at a higher pH. And so that section here where we hit equilibrium is much smaller than if we're going from a strong acid to a strong base. To pick a proper indicator, what you want to know is what pH was that equilibrium established. And you're looking for a pH, an indicator that has a pKa value that is plus or minus 1 from that equilibrium pH. And so you want to look at a table that has the pKa values, or if it has the Ka values, do negative log to determine the pKa values and see if you can find one that's plus or minus. If you can find one that's exactly spot on, then great. Otherwise, plus or minus within that range of your pKa value for the pH here. So now we're going to look at what happens with the pH once we go beyond that equivalence point. And you can see from the graph here that if we have a weak acid, strong base, that's going to moderate up here in the 12 plus range generally. So how do we do that as far as our calculations are concerned? Well, first of all, we're going to take our moles of our sodium hydroxide here, and we're going to get our moles of sodium hydroxide here. So 0.003 moles of the sodium hydroxide, and we're going to also do the same thing down here for our weak acid. So we're going to turn these into liters and multiply to get our mole values. So we have 0.0025 here for moles of that weak acid. And now we need to get molarity for these. So we need to take the new liters because this is now in a solution. So we're going to take the liters here, which would be 55 millimeters, which is 0.055 liters for each of these. And we're going to convert that and get our new molarities. So 0.0545 molar. Nope, sorry. I'm copying down my stuff in the wrong spots here. Let me erase that. Value for this is going to be different. My apologies. This is going to be 0.0455 molar of our weak acid. All right, so now we can put this into our ice table. We have our weak acid, we have our hydroxide ion. We're going to be making some water here, and we're also going to be leaving behind this conjugate base. So this is our molarity for this is 0.0455. Our molarity for our hydroxide is 0.0545, and then of course we'll produce 0.545 here as well. I'm sorry, no, that's a production. My apologies. There we go. We won't have anything here. We're going to subtract then our limiting reactant from both of these. And then this will be a production. Okay, of course we have 0 left here. And this would actually be beyond equilibrium, to be honest with you. And then this is going to be 0.0091. So our concentration
Nikki Shuka, please call 5270. Nikki Shuka, please call 5270. Thank you.
Our production of our hydroxide ion then is going, or our molarity for that is going to be 0.0091 molar. So if we take negative log of 0.0091 molar, then we are going to get the POH. Our POH then is going to be 2.04, and if we subtract that from 14, that's going to give us 11.96. So then if we want to look at kind of some comparisons of these different titration curves, you can see here if we have a weak acid versus a strong acid, our weak acid is going to have a pH that's greater than 1 typically. This one would be 3 here. Your equilibrium, the steep slope here for your equilibrium, your straight up and down line is going to be a much shorter area than versus with a strong acid. They all finish at approximately or at the same pH, but this section here and then where they start out is going to be different. Remember the section in between here where we're at the half equivalence point. So if this occurred at 25, around 12.5, then that point, the pKa or the pH, whatever the pH is here, is going to equal the pKa of that acid. So that's also a good section to kind of keep in mind. That's often a key point that if you can pick up on that in an AP exam, you're going to earn some points. All right, we can also have a third type of titration. This is a weak base with a strong acid. So here we would end up with a titration where you're starting out here, or I guess this one would actually be a strong acid here, or a strong base with a strong acid is this one. And the equivalence point again is at 7. If we compare that to a weak base with a strong acid, this is our buffer region. This is going to be our equivalence point. Again, see how that is a shorter section here with your weak and strong versus your strong. And your equivalence point is not going to be at 7 anymore. Since you've got a strong acid with a weak base, it's going to be less than 7. So things to kind of keep in mind, because the solution begins with a weak base, we expect the initial pH to be higher than 7, and it's going to be a lower number than if we started with a strong base. So there's an initial small drop in the pH as we begin, but then we get that buffering region, which we're going to talk about buffers in the next section. The steep drop then at that equivalence point is going to be smaller than it is when we are looking at a strong base, strong acid. And beyond the equivalence point, it's going to slowly change as we're adding in more of that hydroxide, or hydronium ion, excuse me. All right, so same idea, except this time we're going to have a Kb value. So if you need to figure out if you've got Ka, you can use your Kw over Ka to get Kb. So we would need to use that for this because we're producing the hydroxide ion, so we need to use a Kb value here. Okay. The pH approximately halfway to the equivalence point then is going to give you your pKb, and we can use that in our calculations. So here we are going to calculate the pH of the solution produced during titration following the addition of 12 mils of 0.1 molar HCl to 25 mils of 0.1 molar NH3. This is almost halfway to the equivalence point. So when we are doing this, we're going to turn these into moles again. So 0.025 times 0.1, that's going to give me my moles, which equals 0.0025 moles. And then I'm going to divide that by these two volumes added together, but converted into liters. All right. And so for this guy, we're going to be starting out with 0.0676 molar NH3. And for this guy, we are going to be 0.0012 moles over 0.037 liters. That's going to equal 0.0324 molar HCl. So if we put that into our table here, we've got HCl, we have NH3, we are going with our chlorine, our NH4+. We're going to be starting out with our hydrochloric. We have the molarity there of 0.0324. We have the molarity of the NH3, which is 0.0676. And initially, of course, we don't have any of these. We're going to subtract away our acid here because we have that in the least amount. So that's going to be our limiting reactant. We're going to be then producing, that's a 0.0324 of those. So here in the end, we're going to have 0.0351. That NH3 then is then going to interact with water to produce NH4 plus ion plus OH minus. So we have for this 0.0351, our water doesn't matter. The NH4 we have from up here, we're going to bring that down. That's going to be 0.0324. And this guy is going to be X. So we need to figure out how much of him we're forming, okay? So here we have 0.0351, and we're going to minus X from him. Here we are going to have 0.0324, and we've got X, okay? So our Ka value was given for this. We were given that back in some of our previous work. That was 5.6 times 10 to the minus 10. So if we take Kw over the Ka, that equals our Kb. So Kw, remember, is 1 times 10 to the negative 14. So our Kb value then is going to be 1.8 times 10 to the minus 5. So Kb is going to equal our NH4 plus times X over our NH3. So if we plug in the values that we know our Kb is 1.8 times 10 to the minus 5. We know that our NH4 here is 0.0324. We know that this is X, which we're going to be solving for, and we know that our NH3 here is 0.0351. We can ignore this guy because he's a magnitude enough away, with this being -5. It's far enough away from this that we can't ignore that. And remember, they're not going to make you use the quadratic equation, so it comes down to that in your work. Just understand that you're probably going to be able to ignore it. Now, when you get into college, that may not be the case, but right now for AP it is. So just keep that in mind because time is of the essence for those exams. All right, X is going to equal our hydroxide ion concentration, which we're going to solve for here. So we're going to multiply these two values together. Then we're going to divide by this value. That'll solve for X. That value is 1.95 times 10 to the minus 5. That's not the best penmanship. If I take the negative log of this value, that will then give me my POH. POH will be 4.71. And your pH then, if we subtract that from 100, will be 9.29. Okay, now this is halfway to the equivalence point. Does that make sense? If we're doing a weak base and a strong acid, that pH is going to be somewhere in here. So we figure it's going to be greater than 7, but it's going to be less than what we'd started out from at the beginning, which in this case, that is true. All right, so POH will equal your PKB at that half equivalence point. So if you know what your equivalence point is, if you go backtrack, if you divide that by half, so for this graph here, we had our equivalence point again at about 25 mils. If we backtrack to about 12.5, we're going to be right around in here. And if we go over and find the pH value of that, it's It's going to be 9.75-ish, okay? That 9.75 should equal our PKB. So if we want to take this and figure out what our PKB is, we just take our calculator and do a negative log of that. So 1.8 to the negative 5 equals, I'm going to do a negative log of that value. That equals, that was my PKB. So that was going to equal my POH. And then if I subtract that from 14, that's going to give me 9.25. So this is very close to that value. And they said, right, it's almost halfway to the equivalent. So we're not quite to the equivalence point. The equivalence point, the half equivalence point would be 9.25 for the value. This is 9.29. So we're darn close, okay? Again, we use the graph to figure this out for this. And, you know, you can do that if you're given the graph, and oftentimes you are. So keep that in mind when you're doing your calculations. All right, looking at the next problem then, this one is stage 3. This is pH at the equivalence point. So here we are going to start again, same song, different verse. We are just going to find out our moles here. So 0.0025, that's our moles of HCl. We're going to then divide them by our combined volume, which is 0.05 liters. That's then going to give us our molarity of HCl. And molarity of HCl then is 0.05. Here, it's going to be the same calculation because this multiplied together is that. So we're also going to have 0.05 molar NH3. So if I write my equation down, HCl plus NH3 yields NH4 plus Cl minus. This is 0.05, 0.05. This is going to be 0.05. We're going to subtract 0.05 away here. They're both going to be gone. So we won't have anything left here, and we will have produced 0.05 here. Okay? And also the same thing for our chlorine. So if we take this value, if we take this guy and we put him into our next equation, plus water, he is going to go through, he's going to give us our H plus ion plus NH3 minus. Okay, we have a 0.05 here. Water doesn't count. These would be X and X. This would be 0.05 minus X. And these, of course, are going to produce X. Okay, so these are our ICE tables. Now we can take our Ka value then. So our Ka is going to equal our X squared. So we're going to square these, multiply these by each other, divided by 0.05. Again, our Ka value is such a magnitude because this is a crazy Ka value. Our Ka value here is 5.6 times 10 to the negative 10. So that's so far away that we're not going to need to subtract that X out. Once we multiply by this and take the square root to get our X value, that is going to equal 5.3 times 10 to the minus 6. That is going to equal our hydronium ion concentration, or H plus concentration. We take the negative log of this value, that gives us our pH, which is 5.28. All right. So once we continue with that, again, same idea for picking out indicators. You're going to look at that Ka value of the indicator. You're going to look at the pH at equilibrium and try to find one that is very close to that. Then if we look at pH beyond the equivalence point, we're going to have an excess amount of this hydronium ion concentration. That is going to be so large that it's going to mask anything from this that would be creating hydronium ions in OH ions in that material. So we can just focus on pretty much looking at how much excess hydronium we're going to end up with. And when we do that, we're going to have our NH3 plus our HCl. We are going to form NH4 plus Cl minus, NH4 plus. All right, we're going to calculate our molarity of our HCl. Molarity of our HCl then is going to be 0.003 moles over 25 and 30 is 0.055 liters. That's going to give me a molarity for my HCl that is going to be 0.0545. I'm going to do the same thing here, 0.025 moles over my 0.055 liters is going to give me a molarity for my NH3 of 0.0455. I'm going to subtract 0.0455.
Jake Wheely, please come to Monty's office. Jake Wheely, please join us in Monty's office. Thank you.
Okay, I'm going to have none of this left over. Here I'm going to have 0.0091 left over. This is going to be, I'm going to have produced some of this, but it's going to be so small by the time we react that with water that it's not going to make a difference. This is going to be such a magnitude larger that this is really the only thing that's going to determine our pH. So if that is the concentration, if I take the negative log of 0.0091, that's going to give me a pH equal to 2.04. And then you can just kind of see from some of these examples, we just put some of these examples out here for you to look at this. When you have a diprotic acid, so something like H2SO4, you'll end up having two different equivalence points, and that's because you have two different hydronium ions in there, one cleaving off from the first acid and then one cleaving off from the second. This is an example here of a strong acid, strong base. And then this is another example of one of those diprotic acids. This is actually a polyprotic. So this would have 3 hydrogens that would be able to come off. So you can see from a graph like this that something like that would occur.